You execute a smooth, rhythmic pour over your coffee bed. The setup looks visually flawless, yet the resulting cup tastes aggressively bitter and severely sour at the exact same time. When this happens, the immediate instinct is to blame the pouring speed, the water temperature, or the beans on the counter. But precise brewing technique becomes irrelevant when the initial mechanical input is physically chaotic. Setting your grinder dial to medium does not cleanly slice every coffee bean into uniform, medium-sized pieces. Instead, the output is a chaotic spectrum of particle sizes, ranging from massive, unbroken chunks known as boulders to microscopic dust. The simultaneous bitter and sour taste in your mug is a physical symptom of the grinder's mechanical inconsistency. To see exactly how this failure operates, we have to look at the physical chemistry data. Researchers in Christopher Hendon's lab measure a metric called grinder Wickhamtion, the exact percentage of coffee mass that gets trapped inside the machinery during a normal grind. This chart shows baseline retention rates hovering above 10%, compared against a secondary test group where retention plummets to roughly 1.5%. That dramatic drop is the result of introducing trace moisture, literally a single drop of water added to the beans before grinding. The data shows a massive reduction in trapped particles, which raises a specific question. How does a microscopic amount of liquid alter the mechanical output of heavy metal burrs? To interpret this lab result, we first have to reverse engineer the complex fluid dynamics of water interacting with surface area. In chemical terms, brewing coffee is simply an extraction. Hot water acts as a solvent, pulling soluble flavor compounds out of organic cellular structures. Extraction speed is dictated by surface area. A massive coffee boulder sits next to a microscopic speck of dust and water. The timeline reveals the disparity. The speck surrenders its compounds in seconds, while water barely penetrates the boulder, leaving its core untouched. When a particle surrenders its compounds too quickly, it releases harsh, bitter, and astringent flavors. Conversely, when a dense core remains untouched, it produces a hollow, sour taste. If your grinder produces highly uneven particle sizes, the resulting cup contains both extremes of the flavor spectrum. Look at a cheap blade grinder in slow motion. The bean is violently struck by a blunt metal edge, shattering into hundreds of asymmetrical shards. The machine does not grind or slice the coffee uniformly. It operates as a chaotic impact weapon, repeatedly smashing the fragments into smaller pieces. This violent smashing creates a massive volume of microscopic dust. In the industry, any particle measuring below 100 microns is classified as a fine. A Burr grinder improves on this by forcing the beans through a strictly calibrated physical gap between two steel teeth, ensuring particles cannot exceed a specific maximum size. However, roasted coffee is a brittle, organic material. Even the most precision-machined burrs will still shatter the beans to some degree, producing invisible fines. Sub-100 micron fines are an inescapable byproduct of any mechanical grinding process, and they sit like a microscopic trap inside your coffee bed. When you pour water over that bed of coffee, fluid dynamics take over. Pressurized water will always seek the path of least resistance. As the water flows downward, it picks up the microscopic fines and carries them deeper through the coffee bed. These fines filter down and pack tightly into gaps between the larger boulders, creating a solid barrier. Water hits this blockage and severe pressure builds behind the dam. Eventually, the structure fails and water punches a narrow, high-velocity pathway through the weakest point. This physical phenomenon is known as channeling. The high-velocity streams rush through those narrow gaps, massively over-extracting a tiny fraction of the coffee. Meanwhile, the bulk mass of the bed is bypassed entirely, remaining dry and under-extracted. Channeling is the physical mechanism behind the bitter-sour paradox. Even precise pouring recipes are useless against this kind of chaotic fluid dynamics. If fines are an inescapable byproduct of grinding, we have to ask why they clump together into these dense, channel-inducing blockages instead of distributing evenly throughout the bed. The answer lies in triboelectric charging. When you violently crush dry, roasted coffee beans together, you generate intense physical friction. The grinding chamber acts like a miniature thunderstorm, generating a massive buildup of static electrical charge inside the machinery. The microscopic fines react strongly, acting like tiny magnets, instantly snapping together into dense clusters and clinging to the walls of the grinder. This invisible magnetic clumping is the direct physical cause of grinder retention, and it creates the dense clusters that fall into your brewer and initiate channeling. Static electrical charge forces these fines into localized, destructive blockages, which is the direct cause of a ruined extraction. Watch what happens when a single drop of water strikes the dry surface of a roasted coffee bean. This brings us to the Ross Droplet Technique, a method of intentionally introducing trace moisture to the beans immediately before grinding. The moisture coats the beans and acts as a conductive physical pathway. As the beans are crushed, that pathway safely dissipates the triboelectric static charge before it can build up. This neutralization of static is exactly why the Hendon lab data showed grinder retention plummeting to 1.5%. Without the static attraction pulling them together, the fines refuse to clump. They fall into the brewer and distribute evenly throughout the coffee bed. That even distribution prevents localized blockages from forming. The water flows smoothly through the entire bed, stopping channeling and eliminating the bitter-sour paradox. Before you spend thousands of dollars on precision brewing kettles or expensive espresso machines, you must first control the physical inputs going into them. Mastering the cup requires identifying and controlling the invisible particle physics occurring inside the grinder.